Hi, I'm Jeffrey Bella,
And I'm Christian Brown.
and today we'll be covering
One-Byte
One-Byte Overflows.
So pretty much overview here, we're going to explain one-byte overflow attacks and how they kind of work, and at the same time, we're going to show you a little demo of an attack in the works. And then we're going to show you a recent example of a single byte overflow in modern software.
So you all remember the basic stack and heap buffer overflows, right? Because if you don't, you will be screwed. Stop this video and review them first.
Anyway, in classical stack buffer overflow, our buffer overflow is sufficiently long enough to allow us to overwrite the return address. Then, when the method returns, it goes to our altered return address, giving us control. At that point, you can either execute shellcode within the buffer, the environment, use a return to libc, whatever manner works for you. For instance, let's look at this exploit here, and we put shellcode into the buffer and then overwrite the return address so that it takes us to the beginning of the shellcode.
Oh hey, look, it works. So that was rather easy to break. Maybe we want to try to make it a bit better. So here we have an example where a user tries to fix it by using string length to compare the input, argv1, with the size of his buffer, 1024 bytes. So that makes sense. I think it will work, right?
I mean, it looks safe, but if you look carefully at the documentation for string length, the length it returns does not include the terminating null byte. So, if the hacker gives it a string of the exact buffer length, the terminating null byte will overflow.
Whoa, wait. Is this even exploitable? What can we do with a single null byte overflowing? Let's try it. Let's attack it with a buffer filled with A's. So Python script here that puts in 1024 A's to fill it all up. Let's see what happens. We got a seg fault. Let's see why that occurred. Okay, the seg fault occurred at 4141414141. That is trying to execute something at the address AAAAAAA. I think I said too many A's. Oops.
Let's break down what happened here. Somehow it tried to execute whatever was at an address filled with A's. Let's look at GDB to find out why. So let's check out the store DBB before and after we copy our input into the buffer. Alright. Now checking before the string copy, and as you can see, our EBP is at FFFFD248. And now after, we have, if you can see, the last byte changed to just a single null. So what can we do with this EBP?
When the copy function calls leave prior to returning, the stack pointer is going to be set to the EBP, and then the old EBP will be popped.
So, with our altered EBP, the frame pointer that main gets when copy returns will now be inside the buffer.
When main then leaves itself, because main also does return eventually, we have the stack pointer move to that frame pointer that's inside of our buffer that we were able to make ourselves, and then it also pops nonsense into the frame pointer, as you see at the end of this diagram.
Now main returns, so we'll use whatever the stack pointer is now pointing to, which we have control over as the return address. So we just have to make this point to somewhere in their NOP list.
So to do that would require a good bit of stack math. We're not going to make you do that yourself right here. Instead, we have already done that for you, and we have the exploit built off of it. So we have an op sled followed by the shellcode, and then we've calculated exactly where within our buffer it needs to be, but we have this address right here that points to within our NOP sled. And then following that, we just have some nonsense to fill up the buffer entirely so that we get our 1 byte that overflows. So let's see if it works. Hey, we got a shell! Woo!
Nice. So that was our single byte, null byte overflow vulnerability. Amazingly, single byte overflows can be used in much more than just stack overflows. In fact, think about it can just about any other overflow, like a heap overflow, for example.
Now, you may be thinking, this sounds like a very niche bug to exploit. But this kind of exploit is very prevalent in modern-day web applications, and it can cause devastating effects.
In late September, an article was released outlining an attack on Chrome OS using a single byte heap overflow exploit. Chrome OS utilizes a library called CS453.
Essentially, C-Aries is a asynchronous DNS resolver, a library that is generally used to resolve domain-related issues and find a corresponding IP address. For example, C-Aries itself is used in applications like libcurl and Second Life.
A maintainer for C-Aries was recently notified on a bug from the original version of the library, 1.0, which happened to be carried over in all the updates since 2003 up until 1.11. That means this bug has existed for nearly 13 years, unreported.
This discovered flaw is so disastrous that it allows an attacker to execute code on Chrome OS in JavaScript as the root user.
A 37-page detailed report was submitted to this maintainer detailing how this attack can be executed. Although the report is still confidential, the general methodology is known.
So two functions in C-Aries contain this bug. They don't actually coexist. They're just in different versions. One is the later version of another. Its name changed in a version switch. So here we have the most recent version that contained the bug, Aries create query.
These functions essentially take a name string as input, allocate memory in the heap for the DNS protocol data, and then return the allocated data and its length.
Functionally, these methods work fine, but due to a logical error, the buffer can be used to exploit the DNS resolver. By adding an escape period to the end of the string, say simple string followed by an escape period, we can trick the program to overflow the buffer.
The allocated memory area will be too small for the data, thus allowing a single byte to be written outside said area.
Generally, the DNS resolver will translate this byte to the value 1. Now, what damage could a 1 actually do?
So, the key component the attacker needs to understand is that the Chrome OS utilizes a HTTP proxy. By sending a carefully crafted request through this proxy, you can write a string and overflow a 1 out of the buffer. So, what can we do with this 1?
Chrome OS uses a malloc in order to create an allocated heap space based off of these HTTP requests. The allocated space consists of a header that is followed by the malloc data, like shown at the bottom of this slide.
Thus, in our One-Byte Overflow tag using HTTP request through a proxy, the 1 formed by adding an escape period to our string will be overflowed into the header of the memory block followed. The flag altered is actually code, the one saying that the next area of memory is currently in use. Does this sound familiar? Yeah, that's right. It's a simple heap overflow like we've talked about in class before. The area would be consolidated when the initial block is free. So we have a much larger chunk of combined memory that can be allocated to a new request we make.
So the attacker was able to insert his own commands into this newly freed space, for which a part was actually still in use. Therefore, the proper combination of these bugged allocations could be used to wrest control to the hacker. Although the user would have to be tricked into using particular JavaScript code, this is much easier actually than breaking C-Aries, and it's also outside of the scope of this presentation.
The documentation on this C-Aries attack has yet been released to the public, but when it is, you'll be able to read all 37 pages of the attack. Now, if you can see here, we're showing you how they fixed it. This is within the C-Aries request query. How they fix it was just in the for loop. They checked to make sure that character by character, there's no escaped period occurring. So that's how they fixed it.
This goes to show a single byte overflow attack can be very devastating. Amazingly, such exploits are very prevalent in many common programs today.
So remember, when writing code, check your buffers. Please check your buffers and ensure that no space can be possibly overflowed.
And here we have our sources if you would like to look at them, and we will be taking questions at the live version of this. Again, please check your code for overflows. Bye-bye.